Robbie? I didn't hear what it was, so I don't even know. But are we ready to tackle this thing called section 12.1 with all these heavy backpacks off? At least for this class. Come in, be light, be free, be ready to go. Cool? Here we go. What are we doing? Playing with the table. All right, cool. What are we supposed to doing? Well, we already did the table, plugging in from below, from above. I used the whole, I just started recording, I'm recapping. I used the whole, hey, do your shoes match? And all of you in this classroom right now, maybe one's dirtier than the other, but the shoes match. So I'm saying you can match. So what am I asking you to do when we do limits? See if it matches. Real quick, what do I mean it matches? What does the arrow mean in math? Approaching. Getting closer and closer and closer to, right? So what am I getting closer and closer and closer to? Look at the arrow. See the -3 in the table? Am I getting closer from one side? Can I also get closer from the other side? And what do limits say? From either side. I have to have them agree. I have to have them match. Did this one match? Seemingly. Yeah, and if you went to the -1.667, it was 1.6666666. They seem to match, and I said the equals, and we are totally and completely correct. We're trying to figure out right this second, what the heck? I thought we could take the limit and plug it in. Isn't that what our notes said? Didn't I say down here? Uh-oh, where's my really cool matching page? Oh, no? Oh, here. I lost it. Didn't I tell you come from below A and come from above A, and if they match, yay, the limit. And it was on this one, coming from below, 4, coming from above, 4, and yay, limit is 4. Dun, 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 dun. But this one is different. Is that a problem? I just told you the limit is, but you tried to plug it in, or some of you might have just written that and been like, yay, it's done. But guys, isn't this blank for plugging in -3? And what happens when we plug in -3? I know your calculator told you error, but doesn't that make sense? Because -3 plus 3 over 9, -3 squared, isn't that 0 over 0, which does not exist? So I just had you graph it in your calculator. And when you graphed it, what did you see at, first of all, -3? What's going on there? There's no y because maybe some of you didn't see it. Maybe it's going on at 3. Okay. Did you see an asymptote? Do you remember the parent function, 1 over x? Okay, I'm asking you to remember. Don't pull the backpack back on. Don't pull all the baggage from this year back. Oh, so many life lessons. Back on. This is 1 over x. Maybe you forgot. This is 1 over x. What would, wait a minute. What would 1 over x minus 3 look like? Wouldn't it be this shifted 3 to the, oh. So how do I know that this is going to be something like this without using my calculator? Literally, I gave away my calculator. I can't use it. How'd I know that? Because this was that shifted, boom, 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 3. And what am I going to put right here? A hole. We'll talk about that in a second. Or let's talk about it now. Holes are, review from beginning of the year, removable discontinuities. This is a hole, which is a removable. Do you remember why it was called removable? Discontinuity. Discontinuous. Break. Jump. Hole. Discontinuity. But why is it removable? Oh, because you can go in and pull it. Well, no. It's because of the function. It's because of the function. Guys, Tony, I think you see it. What can you do with this function? What happens when you factor the bottom? And what's true about the top and the bottom once I factor? I can remove. Yeah, but Robbie, you're right, right? Take out, remove. I can remove this factor, and this factor has a 0 of what? -3. This one's stuck, non-removable. X equals 3, I cannot remove. That's a vertical asymptote. But x plus 3, I can take out. That's a hole. This is removable versus non-removable discontinuities from chapter 1 or 2. I don't remember which. So why was I talking about 1 over x minus 3? Because who is this? Everywhere but here. 1 over x minus 3. Anyway, long story short. We have a graph. Are we good with the graph? Asymptote hole. Where would negative 3.1 be on the graph? We plugged it in the function in the table, but where would it be on the graph? Right there. Well, that's negative 3.1. Wouldn't it be like right there? Where would negative 3.01 be? Right there. Where would negative 3.001 be? Right there. Okay. Where would negative 2.9 be? Probably closer, but you guys get the idea, right? There's negative 2.9. There's negative 3.1. Right there. Where would negative 2.99 be? Right there. Where would negative 2.99, negative 2.999 be? Right there. How big is this hole? Even though it's taking up tons of space right now, how big is this hole? It's only at negative 3. And how big is negative 3 if you have negative 2.9, negative 2.99, negative 2.999, negative 3.1, negative 3.01, negative 3.001? Sorry, wrong way. I'm doing it my perspective. Negative 2.9, negative 2.99, negative 3.1, negative 3.01. How big is negative 3? Very small. Do you see it? It's like a slice. And it's a slice that doesn't even have any depth. It's so small, we actually call every point dimensionless. There is no space to it because it literally is one infinitesimally thin slice. I'm sounding so snazzy. But long story short, it's thin. It's really thin. So question. A limit says, where is it headed? And guys, where are all these infinitely many, because I could keep on going, negative 2.999999999. Where are they all headed? The limit is negative 1/6. Why? That's where they're headed. That's where they're approaching. What's going on at negative 3? Well, actually nothing. But I don't care what's going on at. I care what they're getting closer and closer and closer and closer and closer to. Does the limit exist? Yes. Does the point exist? No. But can the limit exist without the point existing? If all I'm answering is where it's headed, where it's approaching. Yes. Let me give you a quick example. Ready? 2 people. I wish I had a specific example for this. Is there any business, food place, etc., that has recently moved and there is a building that is locked where it used to be? Can anybody think of anything? Has anything recently moved? Any of the Blockbusters. I'm not sure if they're anywhere else, though, but good. Good example. That's an interesting fact that I did not know. Anything else besides Blockbuster that literally is no longer here for anyone to go to? Sports Authority. Is there another one? Yeah, anything that's closed and just moved somewhere else to a better location. You know what I'm talking about? Like, okay. Pause. Let's pretend that, we'll do it this way. The In-N-Out, something that you all are very near and dear to, on Balboa and Lassen closes. Something is wrong with the, whatever, they found some endangered species or like there was an oil thing that coming, I don't even know. The whole location closed and moved somewhere else. Let's say they built one, I don't know, where are they building tons of stuff? There's that new Starbucks by the mall, or there's the new Chipotle-ish, it's not new anymore, up there. Anyway. They move it to, can anybody think of a random blank spot of land? North Campus. Ha! Right next to North Campus. There's a whole field. They haven't been able to sell it. They put an In-N-Out right there. I don't know. I'm making up things. Okay, stop. That one closes, locks, chains, can't go in, etc. Okay? The In-N-Out that we all know and love. Closes. It's now right next to North Campus. But not everyone knows it. Okay. You graduate high school. I don't know, we'll pretend this happens. Graduate high school and you call. It's where we always have. In and out. Both headed that one, not realizing it's closed. Where are you headed? You're approaching the same place. Where? The in and out that you went to high school. Always, growing up, whatever, to, right? You call up, graduated, stuff's changed, you didn't realize it, and hey, let's go to in and out. We're both home from college, let's go to in and out. Where are you both headed? In and out. Does the limit exist? Yeah! Where are you going? You're going to the same place. You're going to in and out. Sweet, good job. Limit exists where you're approaching exists. But what happens when you, let's just say you're totally oblivious, you're talking, yeah, you don't realize there are weeds everywhere, and there's nothing. Anyway, you go up to the, oh, there's no place to go up. You go to the window and you're like, yay, let's order. Are you going to get food? Have you converged to the same location? Are you getting food? No. That's very similar to this. This infinitesimally thin DNE, it's so thin, it's not so much like, hey, there was a boom and like the whole place isn't there anymore. It's there, you just can't get in. That one spot you can't get into. -3 you can't get into, but everywhere else is fine. You get all the way up to the window and there's signs and yeah, it's empty, they're cobwebs. Or if you want to, you could think of sometimes. Or you could just, yeah, there you go. But do you guys get the idea? What's a limit? It's an approach. Does it matter whether or not you're going to get your burger? No, it just matters that you're headed to the same place. Well, okay. For the limit answer, no. So, can we come back really quickly to this really important table? And can we change something? Because didn't you guys just see that this is not always right? Okay. Let's change this table just a little bit. The limit equals L if both sides match and both sides are showing approaches from below, technically from below, but I'm running out of space, approach above. So we have the above approach, we have the below approach. If the approaches match, the limit exists, and the limit equals L. But I'm going to go ahead and, see. Can I get it out? I want you to go away. Please go away. Please go away. No! Okay. Life's too short. I don't have time to mess with it, so I'm going to do this, and I'm going to do this, and I'm going to hide him. If I can't get rid of you, I can at least hide you. Okay, there we go. Will the L always be there? Sometimes yes, and sometimes no. But here's the point. It doesn't matter. Doesn't matter. Doesn't matter what's going on. This is the at. But a limit is not necessarily the at. The limit is the approach. Sometimes this will be the same. Sometimes it'll be different. It doesn't matter, though, because the limit just says, hey, do the approaches agree? Where are you headed? Are you headed to the same place? If you're headed to the same place, sweet. Where are you going? In and out. You're going to get your burger? No, but where are you going? In and out. Both of you to in and out. The limit exists, and the limit is in and out. We're not going to be able to keep on talking about in and out, but you guys get the idea? Okay. If you're headed to the same place, limit exists. Done. So graphically, we just talked about a graph. True? Where were we at yesterday? Tables. Well, what is a limit? Boop. And then tables. Boop. And where are we today? Graphs. Boop. There you go. Where are we today? Graphs. Graphically, if you, what's that word? Nice. If you approach on the graph from the right and the left, hey, isn't from the right above, like the table? And isn't the left below, like the table? Graphically, on a graph, if you're approaching, getting closer and closer and closer to, from the right above, from the left below, you are supposed to, X is approaching, look at the, what is L again? What kind of value is L? X is approaching A is an X value. F of X is approaching L is a Y value. Look at the Y values. You got to look up. Ooh, there's a life lesson to that. You got to look up. Why? Some of you, this concept of looking at a graph is going to be confusing because you're supposed to be coming from the left and from the right. You're supposed to be coming from the sides. But as you're trying to figure out what sides, because there are so many different X values you could be coming in towards, if you get focused on the sides and you don't up to the graph, now sometimes the graph might be down, but if you don't look to the graph, you're not going to know the answer. So for the limits, we are looking at the y's. We got to look up for the limits. We got to look at the y's, but we're coming from the sides. We're coming from the sides and we're looking at the y's. So here's an example. We got to come from the sides of who? See it? We got to come from the sides of 1. So we're going to come from, you know how in the table we had to come from below and come from above? So guess what? To know this, we still have to see if it matches. And yeah, I know. We're getting to the graph in a second. And yeah, I know. Well, some of you might see it and some of you might not. So I'm not going to say what I know. Notation-wise, I have to come from below 1. And I have to come from above 1. It's the exact same thing as the table, guys, as far as what we're doing. We have to come from below or from the left, right? Left is below. And then we have to come from above or come from the right. And remember, look at your shoes and have it remind you, unless you start being weird and mismatching. Look at your shoes and have it remind you. What do I need those sides to do? Match. Where's the left of 1 on the graph? Well, 2 ways of doing it, which we could technically do in the table too. We could say, hey, where are you at 1? Oh, you're right here. Sweet. I need to come from this side of you from the left. One way is to go to 1 and say, okay, go a little bit left and then come in towards. But that way, to be honest, can get pretty confusing pretty fast, especially if you get a nasty graph. So instead of saying start at 1 and then go a little bit left, I'm going to say, that's weird. Was there not a hole there a second ago and now all of a sudden there is? Huh, hold on. Lo siento. Keep that as your graph. Instead of saying go at 1 and go a little bit before, I'm going to say no. Don't even think about 1. Think about what would be on the left in a table of 1? 0.9, right? Yeah. Okay. So 0.9, wouldn't that be here-ish? And then 0.99? Then 0.999? Then 0.999? Guys, where are all these? Just think about the approach. Where are 0.9 and 0.99 and 0.999? Where are they all headed? Isn't it closer and closer to the height of 2? They're going to be a little bit below 2, a little bit below 2, a little bit below 2, but they're headed towards 2. And then what if I did 1.1 and 1.01 and 1.001? Where are they headed? Also to 2. Headed to 2, headed to 2. Oh, hey, by the way, what's going on at 1? Oh, it's at 2. Oh, great. This would be a table where sorry, not at 2, at 1. You're headed to 1. Now as you come from below 1, you're going to be heading towards 2. Now as you're coming from above 1, you're going to be headed towards 2. And by the way, what's at 1? Oh, 2. This is one of those tables where they all match. Whatever, it happens. It happens. But what's the overall limit as soon as they match, as soon as they agree, as soon as they're headed to the same place? Your friend could be coming south of Balboa, you could be coming north of Balboa, but you're both headed to In-N-Out, true? So as you head from maybe different directions, but as you head, as long as you're going the same way, the limit exists and the limit is 2. Do they match? Yes. Does the limit exist? Yes. And what is the limit? 2. What did you guys see a second ago? Don't worry. I'll dual page it. What if one tiny little thing changes? Oh, I didn't turn off my sound. I'm sorry. What's different between the f of x and g of x graph?
There's a hole.
There is a hole. But what else is different? Wait a minute. Are we looking at the at? No, we're looking for a limit at the... Oh, we forgot so easily. What's the one word? Approach. Yeah, good. Limit. But as we do the limit, what are we doing? Approaching. So forget the hole. Just ask yourself the approaching. This in and out's open. You're going to get a burger. This in and out's closed. You're going to not get a burger. But are you still going to the same place? Yeah. So guys, what would you answer this one? Even though there's a hole, what's going on as you come from below? It's still going to 2, isn't it? What happens if I ask you what's happening from above? It's still going to 2. Do they match? Yes. So what's the limit? 2. But what's different? Well, if I was making a table, and if I was trying to go to 1, and if I had my x and my g of x, and if I was trying to come from this one saying, yay, I'm going to 2, this one saying, yay, I'm going to 2, and this one saying, error. But what did we see? It's 2. The limit is 2. The approach is 2. You're just not getting your burger. You can be sad, but still have to answer 2. Depression, crushing, although I had that like 3 times the last week. So I'm totally fine not having it for a while. My friend was visiting from New York. There aren't In-N-Outs in New York, in case you're curious. Yeah. Although, isn't there one in like Nevada or something? Or Utah or Arizona, I think, has one. Anyway, not New York yet. So we were there quite a bit. So how about this guy? Let's see if we have this idea down. I want you guys to write the function first. Then I want you to write, hey, we're coming from below, and hey, we're coming from above. But now we're coming from below to... Do you guys want to be lazy and like call him F? Is that okay? Okay, we see him. We see him there. Let's just call him F. 1,000,001 times. Ooh. I'm going to warn you now. My graph is not perfect. Oh, she's not perfect. We should sue. Please don't. None of your teachers are. Hey, neither are you. Anyway, coming back. No. Anyway, I did that backwards. There we go. That's better. My graph is not perfect. Does the graph show the idea? Yes. There's a linear function with a hole at 2. But my graph isn't perfect, meaning you might need to look at the function to find the limit, because my graph is not perfect. It's close. There's a line. There's a hole. It's a little bit off, though. Some of you are like, what's that hole at? Is it at 11? Is it at 12? Is it at 10? How bad was she at making this graph? There's a line. There's a hole at 2. That's the general idea, but my graph is a little off. Can you guys figure out how to use either your calculator or your algebra to figure out the limit perfectly, even though my graph doesn't exactly show where the hole is? Is the hole supposed to be there or there or there or there? How off am I? Well, this gives you all you need to know. Ready, set, powwow. Ready, set, powwow. Meaning, put your brains together. Discuss, talk. Stop, stop, turn. And if you're doing something to think about it, say it out loud. Hopefully not all at once. Go. You have everything you need to know. So sorry. Don't worry, Gavin, I was covering my mouth. Kyle, Rachel is working on your 10-6 to 10-8 quizzes. Don't bug her. Can I just hear what you're talking about? I heard someone say plug into. Plug into value to the graph. Isn't it an error, though? Isn't it one of those tables where it's an error?
Yes.
Oh. But if you get real close, how can you get real close on your calculator? Can you get real close on your calculator? With a table, that's one way. So I heard plug in 2, and then I heard it doesn't exist. Oh, well, if we're plugging in 2. Guys, remember how sometimes it's good? But didn't you guys just, or I just told you, but you guys saw it though, right? If you plug in 2. So is this the answer? Can I? No, not necessarily, because don't you see it agreeing? I think the limit exists. I think it's a number. Again, it's not there. So Kyle was saying if you look real close. So how'd you get real close, Kyle?
Well, I did second value.
Uh-huh.
I did 2.01. Divided, I got 12.03.
So guess what? He didn't even go to the table. I mean, he thought about the table, getting closer and closer. But what did you plug in? You plugged in 1 point. 2.01. So he was kind of doing this sort of thing. Did anybody do this sort of thing? Or maybe some of you were like the same thing. If I find one, I find both. That's good, saving yourself time and effort, right? But if you have your function, how high does it go? Oh, it goes pretty high, huh, guys? So with your window, maybe you had to go a little bit higher than where you were. Okay, so Kyle, you went to value. Does everybody know there's a shortcut to value? Because he was saying go second trace to value. But there's a shortcut. If you're on your graph, you can just hit the trace button, and you can plug in something like 2.01. And you can say, where are you? Oh, don't worry. This is my fault. Do you guys see how that's a shortcut? It's kind of cool. 12.03, right, Kyle? Okay, some of you guys need to practice that again. What if I wanted 1.99? Just hit the trace button. Hit the trace button. Good. Now 1.99, type in 1.99, 11.97. Okay, so what do you think? Where do you think? I mean, just, guys, whew, look at you guys. You're shortcutting already with limits. Why not 1.9, 1.99, 1.999, 1.999? Where is it headed? What? Probably yes. It's headed to 12. So my was a little bit off, but the top one's headed to 12. So what's my limit? 12. This answer is 12 because they match. True? But it was one of those error-y guys. Now, let's see how you guys do, because this is going to help you as to where we're headed at the end of homework. Question. Did anybody not use the graph and not use the calculator and still figure out 12? Adam, how?
I just thought about the whole thing.
I give one. How can we figure out something as a whole? What am I doing right now? I'm plugging in this guy, right? what happens when I plug in? Isn't that 12 minus 12? Isn't that? Do you guys remember in chapter 1 or 2 when we talked about holes, there was infinite form for vertical asymptotes and indeterminate form for holes. Both of them showed zeros in the, but this was different. Holes always happen when you have a 0 over a 0. Vertical asymptotes always happen when you have a number over 0. And what does that indicate? A shared factor, a shared 0. A shared 0 can always be removed. Hole. So Adam, keep going. He's talking about removing, taking away, but I just wanted to show you, you can know it's a hole by plugging in and what happens. Okay, sorry, keep going, Adam.
I expanded the x squared minus 4.
To be?
X plus 2x minus 2.
And then?
And then I moved the x minus 2 and then plugged 1, 2.
That, or I should say, this function is the exact same as this function, except I had to say, oh, well, you know what? Remember, I know I took them away, but this can't happen. So as you're drawing this, you have to put a hole 2. But those are the exact same thing. Just this one says, ooh, 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 add this. Sure. Add this. If that one's the same as that one, just remove that. Can't I just ignore this for a second and say, hey, where would you have been? Yeah, I get it. You can't be there, but where would you have been? So then 3 times 2 plus 2 is, did you even need a calculator to do this? And does it get you the right answer? Yeah. Aha! So maybe there's a shortcut to the shortcut? Wait, I don't really know what the shortcut. Well, the shortcut was saying they're the same place. Like, yeah, we got 12. But if you're good at algebra, couldn't this be even shorter? Like, oh, take away the hole and plug in. 12. Okay, let's go on. So when do limits not exist? We've said the limit exists, the limit exists, the limit exists. You're both going to in and out. The limit exists. There's a hole. The limit exists. So, mean girl time. When does the limit not exist? It's an old movie. Are we that removed? How many of you guys have not? How many of you guys have seen Mean Girls? Oh dear. That's all right. It's cheesy. There's a math competition. There's a girl at the end, and she's like between the other girl, and they basically treat girls like totally dumb in calculus, which I'm a little offended at, even though the teacher was a lady, so it's a little bit better. Yeah, you did. That's the part you remember. Anyway, the limit does not exist. It was a thing. When does the limit not exist? Does D, not N, exist? E, D, N, E. When? Approaching from either side, each side yields different results. Infinity part or oscillates between two fixed values as you approach. It is, and it's hard. But there are some weird functions where if you zoom in, zoom in, zoom in, zoom in, zoom in, it just gets worse and worse and worse, and it's going faster and faster and faster. We're not going to draw comparisons right now, but yeah, some interesting theories about other things that behave that way. Oh dear. Look up string theory and parallel universes, then get really mind blown. Anyway, or just watch sci-fi and be like, this comes from somewhere. Some people actually think this is true. Anyway. Okay, so I will somehow connect with you after I watch it about math. Got it. If you guys want to see what I mean, if you get bored and you get to the end of this, you can plug in the function sine of 1 over x and you can zoom in, zoom in, zoom in, zoom in to 0, 0, or zoom into 0, and see if it seems to get nicer or worse as you zoom, as far as getting closer and closer to a nice little, oh, hey, they are or they aren't approaching. If you're curious about that whole oscillating thing, you can plug in sine over x and zoom in, zoom in, zoom in, zoom in. And don't do it a couple times, because sometimes your calculator freaks out and says, I give up. But then if you keep on zooming, it'll eventually try to show you what's really going on. And if you zoom in, zoom in, zoom in, zoom in, eventually look at your window and see how small your x's have become and how you should be able to see them going towards or away from each other. And as you do that, I'm going to go ahead and I've already used the letter B, so I'm going to use, or A, sorry, so I'm going to use the letters like, I don't know, B and C on my graph. For this one, if we were to use the in and out example, I know guys, I'm going quick. But if we were to use the in and out example, if I was to come from below A, that means from the left of A, this guy says, oh yeah, I'm getting closer and closer and closer to B. This dude's going to the old in and out. Only one of the people didn't know. Positive. The other guy is going to the new in and out location at North Campus. Are they going to the same place? The limit does not exist. This one, are they going to the same place? No, the limit does not exist. This one, are they going to the same place? Yes, but is it a number? No, so we call it DNE, but we actually answer infinity. It's a little awkward, a little weird. And this one, if you guys look at it, super DNE. If you guys see piecewise functions in your homework, can you graph on your graphing calculator and cut off and think about it, and then cut off and think about it and see whether they match or whether they don't? I think so. Bye, cool kids. I'll see you later. We have one more day, but this can get you through. They are like barcodes.
When graphing is actually supposed to show the